Hey folks, 13.1, comparing three or more means, one-way analysis of variance. So the first thing to point out would be analysis of variance, ANOVA. ANOVA, okay. Let's see, remember we did box plots way back in the day? Box plot might look something like that. Low, median, high, Q1, Q3. Our book likes to draw it without the little endpoints, so they might draw it. They put little dots. Just depends on which software package you're using, so it might look something like that. Maybe you have another one that looks like that. Okay, so then let's say here we have an example of three different groups, right? Here's the X bar for this group, the mean, the X bar, the mean, the mean. So the question is, here's three different situations. Is it possible that these groups all have the same mean? So for example, is it possible maybe that they all have the same mean, which is like this location right here? Is that possible? Seems reasonable. Seems like they could all have the same mean. So that's what ANOVA of analysis of variance is, the ANOVA is. If you have three or more groups, do they all have the same mean? So we did something similar when we had that chi-squared, the homogeneity of proportions. So this is basically homogeneity of means. Are the means all the same? So it's going to be very, very analogous. Okay, so we do have some minimum requirements, of course. So the minimum requirements, each sample is a simple random sample. Yep, SRS. Independent, so what I sample from this group has no effect on what I sample from that group. Normally distributed populations, so usually I always say assume we're sampling from a normally distributed population. And the populations have equal variances or standard deviations. So you see how in these three pictures I didn't draw something that had a really gigantic spread. You see how the standard deviation of this data looks like about the standard deviation of this data, about the same as this. The standard deviation, right? Standard deviation describes how spread out data is. Standard deviation of this data is way bigger than those three groups. So I might not be able to do an ANOVA since this standard deviation or variance, which is standard deviation squared, is so much different than those three. Okay, so to greatly oversimplify things, as I always do, I just say, let's assume the minimum requirements are met for all the problems on this worksheet. Sounds good. Okay. So then we go to our first problem. And let's see. So we have three groups, Group A, Group B, Group C. Let's assume minimum requirements are met. And let's read the problem. Assume the data in A, B, and C are independently drawn random samples from normal populations. Are the means of the three populations equal? Are the means of three populations equal? So we have three or more groups. Are the means equal? So similar to homogeneity of proportions, hopefully you would say, oh, so does mu1 equal mu2 equals mu3? If there is a fourth group, equals mu4. Aha! Now the alternative hypothesis, HA or H1 as our book calls it, very similar again to the homogeneity of proportions. We didn't say that all those need to be different from each other. We just said that at least one must be different. So at least one mean is different. Again, we don't need them all to be different from each other. This guy different than this guy, different than this guy. In order to make this null not true, all we need is just one of them to be different. Okay, so at least one mean is different. Okay, yeah, this is kind of just like that homogeneity of proportions. Test stat. Okay, figuring out the test stat, super duper complicated, unless you have a calculator. Okay, so as long as you have a calculator, it's pretty easy, as with most things in life. So we're going to have to put the data into three different lists. So go to Stat, Edit, Enter. List 1, L1. Oh, there's already some junk data there. Let me clear it. Go up so L1 is highlighted. Hit Clear. Let me see if we can even see what's going on here. Kind of, not really. Okay, we'll pretend you can kind of see that. So I go up to L1, so it's highlighted, hit clear, hit enter. Now list L1 is nice and blank. I'm going to give it the data. It was 4, enter, 4, enter, 5, enter, 5, enter, 6, enter. And then do the same thing for L2 and L3. You might need to clean or clear L2 and clear L3. I actually put the numbers in before I started the video because I'm so prepared. Okay, so you put all your data in. And now we're going to have to do a stats test. So I'm going to go to, so once all your data's in, L1, L2, L3, then I go to stat, tests. This new test is called a NOVA. I think it's the very last one, so I'm going to sneak and go that way. Oh, a NOVA, snap, hit enter. And now I'm just going to give it list L1, comma, L2, comma, L3. So you see above 1, it says L1, so I got to hit the second function, so second 1, so it says L1. Comma is right above 7 on my calculator, comma. Give it L2, L2, comma. Give it L3, second 3. End parenthesis, so a NOVA of L1, comma, L2, comma, L3. And it's just going to do everything for me. Back in the day, this would have taken me probably 20 minutes, and I probably would have made a mistake. So Viva Technology, enter. Boom. Okay. It just spits out all the information for us. So test stat, we've seen Z, we've seen T, we've seen chi-squared. Now we have F. So write down what it is. F is equal to 2.5787, 579 when I rounded to the thousands for no particular reason. Right below that it says P, so that's my P value, 0.10899. Let's call it 0.109. Keep it simple. Okay, so it's the same game we've always been playing. Alpha is 0.5, so how does this 0.109 compare to my alpha of 0.05? It's greater than. If my p-val is greater than my alpha, I would say do not reject HO. Fail to reject HO, do not reject HO. Our book says do not reject HO. Other books often say fail to reject HO. Same thing. Conclusion in English. Okay, so either evidence suggests or not enough evidence to suggest. If I say do not, then it's not enough evidence to suggest the H1, the HA, the alternative. Put this in English. Oh, it already is? Okay, not enough evidence to suggest that. And then also copy it. Just rewrite it. At least one mean is different. Cool. So hopefully you're starting to see that we're doing the same things over and over again. There's a null, right? And then there's an alternative. And then you throw the data into a calculator and it spits out a p-val. And then based on that p-val, we either reject this null or fail to reject it. And that's what we just keep doing over and over again. Okay. Hope that made sense.